Hello, and welcome to the Sleepy Cosmos, a cozy corner of the universe where science whispers gently, curiosity is celebrated, and drifting into peaceful sleep is part of the adventure. Tonight, we're embarking on a calming yet fascinating tour through our very own solar system, a softly glowing trail leading us past 8 remarkable worlds, each orbiting the same brilliant heart, our Sun. From Mercury's scorched surface to Neptune's serene depths, each planet has a unique tale, distinctive mysteries, breathtaking beauty, and silent rhythms. You don't need a spacesuit or a rocket for this journey. All you need is a comfy pillow, quiet surroundings, and perhaps a warm, calming drink. As we gently drift through space tonight, you might find yourself wondering, why does Uranus spin sideways? How can Jupiter sustain a storm that's outlasted centuries of human history? Before we set off, if our peaceful voyages through the cosmos brings comfort to your evening, please consider giving this video a gentle thumbs up or subscribing. It's completely free and helps this little celestial journey continue. I'd also love to hear from you. Where are you tuning in from tonight? Are you nestled under blankets beneath Vermont's midnight stars, welcoming dawn's stillness in Tokyo, or simply tucked in your favourite cozy spot? Wherever tonight finds you, you are warmly welcomed here. Remember, there's no final destination or test waiting, just a gentle exploration through space, soothing your mind along the way. So now, if you haven't already, gently close your eyes, take a slow, deep breath, and allow the quiet of space to settle around you like cosmic stardust. 1 luminous star, 8 enchanting worlds, and you, softly floating in between. Let's begin exactly where everything starts, with the Sun. As we begin our journey through the solar system, we start with the Sun. The Sun is a G-type main sequence star, classified as a yellow dwarf. It is composed primarily of hydrogen, about 74%, and helium, about 24%, with trace amounts of heavier elements like oxygen, carbon, neon, and iron. It formed around 4.6 billion years ago from the gravitational collapse of a portion of a molecular cloud. As the material condensed under gravity, it heated up and eventually began nuclear fusion in its core. That process, the fusion of hydrogen atoms into helium, continues today, powering the Sun and producing the light and warmth that reaches Earth. The Sun accounts for 99.86% of the total mass of the solar system. Its gravitational pull keeps the planets, asteroids, comets, and other objects in orbit. Without its presence, the solar system as we know it would not exist. Despite its vital role, the Sun is an ordinary star. In the context of the universe, it is unremarkable in size, brightness, and lifespan. And yet, for us, it is everything. Tonight we'll explore what the Sun truly is, not as mythology, but as matter. As a machine of gas and gravity, light and time. The Sun is structured in distinct layers, each with unique properties and functions. At the core, where temperatures exceed 15 million degrees Celsius, nuclear fusion occurs. This process converts hydrogen into helium and releases vast amounts of energy. That energy radiates outward, fueling the solar system. Surrounding the core is the radiative zone. In this region, energy moves outward very slowly, through a process called radiative diffusion. A single photon can take thousands to millions of years to travel from the core to the next layer. Above the radiative zone is the convective zone. Here the temperature is cooler and energy is transported by convection. hot plasma rises, cools, and sinks again. This motion creates patterns on the Sun's surface and drives much of its activity. Beyond the convective zone lies the photosphere. This is the surface we see from Earth. It's around 5,500 degrees Celsius and appears as a glowing golden disk in the sky. Above that is the chromosphere and finally the corona, the Sun's outer atmosphere. The corona is unexpectedly hot, reaching temperatures over 1,000,000 degrees Celsius. Scientists are still studying why this is so. During solar eclipses, the corona becomes visible as a halo of pale light, shimmering and uneven. The energy that leaves the Sun's core eventually reaches Earth in the form of sunlight. Sunlight includes visible light, ultraviolet radiation, and infrared energy. These waves travel across 150 million kilometers of space in about 8 minutes and 20 seconds. This journey is fast. Light moves at nearly 300,000 kilometers per second. When sunlight reaches Earth, it warms the surface, fuels photosynthesis in plants, and influences the climate. It even regulates human sleep cycles by helping control melatonin, a hormone connected to the circadian rhythm. Solar radiation is also responsible for weather patterns. Warm air rises and mixes with cooler air, driving wind and precipitation. Without the sun, our planet would be a frozen dark rock, uninhabitable and silent. Solar panels, which convert sunlight into electricity, are one way we harness this energy. They use photovoltaic cells to generate power, making solar energy a renewable and increasingly important resource. And while the sunlight feels constant, it actually varies. The Sun goes through an 11-year solar cycle, marked by changes in sunspot activity and solar flares. The Sun is not just a source of light, it is also a dynamic, ever-changing object. Its magnetic field generates solar activity, including sunspots, solar flares, and coronal mass ejections. Sunspots are darker, cooler regions on the photosphere caused by magnetic disturbances. They can last days or even weeks. Solar flares are sudden bursts of radiation caused by the release of magnetic energy. They can affect satellite communication, GPS systems, and power grids on Earth. Coronal mass ejections, or CMEs, are large expulsions of plasma and magnetic field from the Sun's corona. When directed toward Earth, they can cause geomagnetic storms and intensify auroras, the northern and southern lights. The Sun's magnetic field also drives the solar wind, a stream of charged particles that flows outward through the solar system. These particles interact with planetary magnetic fields and atmospheres, shaping space weather. Monitoring solar activity helps scientists predict these events and prepare for their effects on technology and space exploration. Stars, including the Sun, go through life cycles. The Sun is currently in the main sequence phase, which is stable and long-lasting. It has been in this state for around 4.6 billion years and will remain here for about 5 billion more. During this time, hydrogen in the core is steadily converted into helium. As hydrogen becomes depleted, the core will contract and heat up, while the outer layers expand. Eventually, the Sun will become a red giant. It will swell, possibly engulfing Mercury, Venus, and even Earth. The outer layers will drift away, forming a planetary nebula, a glowing shell of ionized gas. What remains will be a white dwarf, the dense, hot core of the former star. It will gradually cool over billions of years, fading slowly into darkness. This cycle is typical for medium-sized stars. More massive stars may end in supernova explosions, while smaller ones fade more quietly. The Sun's transformation will mark a profound change in the solar system, but it is far off in the future. Humans have studied the sun for millennia. Early civilizations tracked its movement across the sky, built calendars around its patterns, and created myths to explain its power. Ancient cultures such as the Egyptians, Greeks, and Aztecs worshipped the sun as a deity. Modern science, however, studies the sun using telescopes and spacecraft. Observatories like SOHO, Solar and Heliospheric Observatory, and NASA's Parker Solar Probe gather data from space, observing solar activity up close. These missions help us understand how the sun influences Earth and the broader solar system. They provide insight into solar cycles, sunspot behavior, and space weather phenomena. On Earth, solar telescopes, often positioned in high altitudes or dry regions, allow astronomers to examine the photosphere, chromosphere, and corona in detail. This research is essential. It not only advances our knowledge of the sun, but also helps protect technology and astronauts in space. And while much has been learned, many mysteries remain. Why is the corona hotter than the surface? How exactly are solar flares triggered? What role does the sun's magnetic field play in long-term climate trends? These are questions scientists continue to explore. The sun plays a direct role in sustaining life on Earth. Photosynthesis, the process by which plants convert sunlight into energy, is the foundation of most ecosystems. It provides oxygen for animals and humans, and fuels the food chain from the bottom up. Seasonal cycles, spring, summer, autumn, and winter, are caused by Earth's tilt and orbit around the sun. These changes influence plant growth, animal behavior, and even human culture. The sun also affects biological rhythms. Humans, like many animals, have internal clocks called circadian rhythms. These are synchronized by the light and darkness created by Earth's day-night cycle. Lack of sunlight can lead to disorders such as seasonal affective disorder, SAD, a type of depression that occurs during darker months. Vitamin D, important for bone health and immune function, is produced in human skin through exposure to ultraviolet light from the sun. From the molecular level to the global scale, the sun's influence is constant and profound. Beyond science, the sun has long held symbolic and cultural meaning. In many ancient religions, the sun represented life, strength, and creation. The Egyptian god Ra, the Hindu deity Surya, and the Japanese sun goddess Amaterasu are just a few examples of solar deities. Structures like Stonehenge in England and Chichen Itza in Mexico were aligned with solar events such as solstices and equinoxes. These alignments helped early humans track seasons and plan agriculture. In art, the sun has been depicted as a source of inspiration, light, and power. It appears in countless paintings, stories, and poems throughout human history. Even today, solar symbolism is used in flags, logos, and architecture. It represents renewal, clarity, and illumination. This cultural connection reminds us that the sun is not just a physical object. It is a presence, both real and symbolic, that has shaped our understanding of time, life, and the universe. The sun is located in the Orion arm of the Milky Way galaxy, about 26,000 light-years from the galactic center. It orbits the galaxy once every 225 to 250 million years, a journey known as a cosmic year. During this time, the solar system moves through different regions of space, encountering clouds of gas, dust, and cosmic radiation. Compared to other stars, the sun is of average size and brightness. It is not a binary star, and it lacks planets as massive as some found in other systems. Yet its relative stability has allowed life to develop and thrive on Earth. Our sun is one of over 100 billion stars in the Milky Way. It is also just one of trillions of stars in the observable universe. Despite this, its light reaches across space to warm a small blue planet. the only one known to support life. Its steady presence is a reminder of both how vast the universe is and how intimately we're connected to it. As we conclude our visit with the Sun, we reflect on its role in our journey. It is not only the centre of the solar system, but the reason the system exists. Its light enables life, its gravity keeps the planets aligned, and its energy drives the rhythms of Earth. Though it may seem distant, the Sun is part of your everyday life. It rises and sets, marks the hours, and shapes the seasons. Its influence is subtle but constant, from the warmth on your skin to the power that lights your home. And while it is a sphere of plasma, billions of kilometers away, it is also a companion. It anchors the world you know and fuels the dreams that reach beyond it. As you rest tonight, let this knowledge be a comfort. You are part of a system that is vast, ancient, and deeply connected. In the next chapter, we'll travel to the first planet from the Sun, Mercury, and explore a world of extremes. But for now, close your eyes and let the Sun's steady light guide you gently towards sleep. In recent years, space agencies have launched advanced missions to learn even more about the Sun. NASA's Parker Solar Probe, launched in 2018, is flying closer to the Sun than any spacecraft before it. It is studying the solar corona, measuring solar wind particles, and mapping magnetic fields. The European Space Agency's Solar Orbiter, launched in 2020, complements this mission. It captures high-resolution images and studies the Sun's polar regions, which are difficult to observe from Earth. Together, these missions are helping scientists understand solar dynamics, improve space weather forecasting, and uncover the mechanisms that power solar storms. This growing body of knowledge deepens our appreciation for the star at the centre of our system. It reminds us that even something as familiar as the Sun still holds many secrets, and with every new discovery we learn a bit more about the universe, and about ourselves. Mercury is the closest planet to the Sun. Named after the Roman messenger god known for speed, it completes one orbit around the Sun in just 88 Earth days. Despite its proximity to the Sun, Mercury is not the hottest planet in the solar system. That distinction belongs to Venus due to its thick atmosphere. Mercury, by contrast, has almost no atmosphere at all. Its thin exosphere is made mostly of oxygen, sodium, hydrogen, helium, and potassium. With no atmosphere to retain heat, surface temperatures on Mercury fluctuate dramatically. During the day, temperatures can soar to 430 degrees Celsius. At night, they plunge to minus 180 degrees Celsius. These extremes make Mercury a planet of harsh contrasts, a world of fire and frost. Mercury is also small. It is the smallest planet in the solar system, with a diameter of about 4,880 kilometers, just slightly larger than Earth's moon. In fact, Mercury is often compared to the moon because of its cratered surface and lack of weather. Its surface tells a story of intense history. Craters, ridges, and plains stretch across the landscape, many unchanged for billions of years. Mercury's movement through space is unique among the planets. It has an unusual rotational pattern. Mercury rotates very slowly on its axis, once every 59 Earth days. However, because of its fast orbit and slow spin, one day-night cycle, a solar day, on Mercury lasts about 176 Earth days. This means if you were standing on the surface, the Sun would rise very slowly, arc across the sky, and set in a manner unlike anything on Earth. In some regions, the Sun would appear to pause and even move backward briefly due to the orbital dynamics. Mercury's orbit is also highly elliptical. it brings the planet as close as 46 million kilometers to the Sun at its nearest point, perihelion, and as far as 70 million kilometers at its most distant point, aphelion. This elliptical orbit causes Mercury to receive varying amounts of solar radiation throughout its year. The planet's tilt is almost non-existent, just 0.034 degrees, meaning there are no significant seasons. Unlike Earth, where the axial tilt creates seasonal variation, Mercury has a consistent solar exposure based purely on its distance from the Sun during orbit. Mercury's surface is heavily cratered, resembling Earth's moon. These impact craters were formed by collisions with asteroids and comets early in the planet's history. One of the most prominent features is the Caloris Basin, a massive impact crater about 1,550 kilometers wide. It was created by a large asteroid impact over 3.8 billion years ago. The energy released caused ripples and fractures on the opposite side of the planet, known as weird terrain. Surrounding the craters are plains formed by ancient volcanic activity. These smooth regions suggest that lava once flowed across the surface, filling older impact basins. Long, curved cliffs called scarps also mark the terrain. These features formed as Mercury's interior cooled and contracted, causing the crust to buckle and fold. Some scarps stretch for hundreds of kilometers and rise over a kilometer high. Unlike Earth, Mercury shows no signs of current tectonic or volcanic activity. Its geological activity likely ceased billions of years ago, preserving the surface as a record of early solar system history. Beneath Mercury's rocky crust lies a large metallic core. This core makes up about 85% of the planet's radius, proportionally larger than that of any other planet in the solar system. The core is believed to be composed mostly of iron and nickel. Recent data suggest that at least part of the core remains molten, which contributes to one of Mercury's surprising features, its magnetic field. Mercury is the smallest planet with a magnetic field. Discovered by NASA's Mariner 10 spacecraft in the 1970s, this field is about 1% the strength of Earth's. It is likely generated by a dynamo effect, the motion of conducting fluid in the planet's outer core. The magnetic field interacts with the solar wind, creating a miniature magnetosphere. Unlike Earth's well-structured magnetosphere, Mercury's is highly dynamic and compressed due to its proximity to the Sun. These interactions can produce magnetic storms and particle precipitation onto the surface, particularly near the poles. Mercury does not have a traditional atmosphere. Instead, it has an exosphere, an extremely thin layer of gases held loosely by gravity. The exosphere is composed primarily of oxygen, sodium, hydrogen, helium, and potassium. These elements come from interactions between the solar wind and Mercury's surface, as well as micrometeoroid impacts that release particles from the crust. Because the exosphere is so sparse, it cannot regulate temperature or support weather. Each atom in the exosphere travels a ballistic trajectory before either escaping into space or settling back onto the surface. Scientists study the exosphere to learn more about surface composition and space weathering. Instruments on spacecraft like Messenger have detected variations in the density and composition of the exosphere based on time of day and solar activity. Despite its simplicity, the exosphere provides insight into the complex interactions between planetary surfaces and space environments. Mercury has been visited by only a few spacecraft due to its proximity to the Sun and the difficulty of entering orbit around it. The first mission to explore Mercury was NASA's Mariner 10, which flew by the planet 3 times in 1974 and 1975. It provided the first close-up images and revealed the presence of a magnetic field. In 2011, NASA's Messenger spacecraft entered orbit around Mercury. Over 4 years, it mapped the entire surface, studied the magnetic field, and analysed the planet's composition. Messenger discovered water ice in permanently shadowed craters at the poles and confirmed the presence of volatile elements like sulfur and potassium. The European Space Agency and Japan's JAXA launched Bepi Colombo in 2018. It is a dual spacecraft mission currently en route to Mercury. Upon arrival in 2025, it will study the planet's surface, magnetic field, and exosphere in greater detail. These missions have significantly expanded our understanding of this small, dynamic world. One of the most surprising discoveries on Mercury is the presence of water ice. Although surface temperatures can become extremely hot, the planet's poles contain craters that are permanently shadowed. These areas never receive direct sunlight, allowing temperatures to remain below freezing. Radar observations from Earth first suggested the presence of ice. Messenger later confirmed these deposits using neutron spectrometry and reflectance measurements. The ice is found in relatively pure concentrations, often beneath a thin layer of dark material that may act as an insulator. Scientists believe the ice was delivered by comets or water-rich asteroids over billions of years. It may also have formed from hydrogen and oxygen released from the surface and trapped in cold traps at the poles. The existence of water ice on such a sun-scorched planet challenges assumptions about where volatile compounds can exist in the solar system. As the innermost planet, Mercury plays a unique role in the architecture of the solar system. Its small size and lack of moons distinguish it from the gas giants and even other rocky planets. Mercury is also the most metal-rich of the terrestrial planets, with its large core contributing to its high density. The planet's orbit is influenced by the Sun's gravitational pull more than any other planet. This causes measurable shifts known as orbital precession, changes in the orientation of Mercury's elliptical path. In the 19th century, discrepancies in Mercury's orbit puzzled astronomers. These were later explained by Einstein's theory of general relativity. Mercury's motion provided one of the first confirmations of the theory. Because of its location, Mercury receives intense radiation and solar wind exposure. This makes it an ideal laboratory for studying interactions between a star and a planetary surface. Though often overlooked, Mercury's behavior helps scientists understand planetary formation, orbital dynamics, and stellar influences. Mercury is visible from Earth without a telescope, but it can be difficult to observe. Because it orbits so close to the Sun, Mercury appears low on the horizon shortly after sunset or just before sunrise. It is best seen during periods called greatest elongation, when it is farthest from the Sun in the sky. The planet appears as a small, bright point of light. Its visibility depends on the observer's location, weather conditions, and time of year. Mercury is more easily seen from locations with flat, unobstructed horizons. Observing Mercury through a telescope reveals phases, much like those of the Moon. These phases result from the planet's changing position relative to Earth and the Sun. Ancient astronomers tracked Mercury's motion with great care. Its fast orbit and fleeting appearances led some early cultures to believe it was two separate objects, one visible in the evening, the other in the morning. Today, amateur astronomers still enjoy the challenge of spotting Mercury during its brief appearances. Mercury is a planet of contrast and curiosity. Its small size, slow rotation, and lack of atmosphere make it a place of extremes, both in temperature and terrain. Yet despite its harsh environment, it remains a subject of scientific interest. The planet's large iron core, ancient surface, and magnetic field challenge many assumptions about planetary development. Discoveries of water ice and exospheric interactions add to its mystery. Through spacecraft missions and observations from Earth, scientists continue to piece together Mercury's history. Every detail helps build a clearer picture of how the solar system formed and evolved. For all its proximity to the Sun, Mercury often escapes attention, but it is a valuable part of the planetary family, an enduring ember at the dawn of the solar system. As we continue our journey, we will travel outward to the next world in line, Venus, a planet shrouded in clouds with secrets hidden beneath its dense atmosphere. For now, rest your thoughts on Mercury's quiet, cratered plains. Let your mind drift through the stillness of a world where time moves slowly and the sun dominates the sky. Mercury's characteristics have also contributed to scientific models beyond astronomy. Its orbital precession was one of the earliest tests of general relativity, a theory that reshaped physics in the 20th century. Precise measurements of Mercury's orbit showed a small deviation from Newtonian predictions. This discrepancy matched the predictions made by Einstein, lending support to the concept of curved space-time. In planetary science, Mercury's high metal content raises questions about its formation. One hypothesis suggests it once had a thicker outer shell that was stripped away by a massive impact or intense solar activity. Another theory proposes it formed from metal-rich material close to the young Sun. Models of planet formation must account for Mercury's unusual composition and structure. Studying this planet helps refine our understanding of how terrestrial planets come to be, and why they differ. In this way, Mercury is more than a planetary object. It is a key piece in the broader puzzle of planetary science and the evolution of our solar system. As our exploration of Mercury concludes, we pause to reflect on the planet's quiet resilience. Though small and often overlooked, Mercury offers profound insights into the solar system's earliest chapters. Its preserved surface, magnetic field, and orbital behaviour make it a planet worthy of study and appreciation. In the stillness of space, Mercury continues its timeless path around the Sun, a steady ember glowing at dawn. In the next chapter, we will enter the thick clouds and high-pressure atmosphere of Venus, a world as different from Mercury as any could be. Venus is the second planet from the Sun, and the closest in size and composition to Earth. Often referred to as Earth's twin, it has a similar diameter, mass, and internal structure. However, beneath the surface similarities lies a world that is dramatically different. Venus is enveloped in a thick atmosphere composed primarily of carbon dioxide, with clouds of sulfuric acid. This dense blanket traps heat through a runaway greenhouse effect, making Venus the hottest planet in the solar system. Surface temperatures can reach up to 465 degrees Celsius, hot enough to melt lead. The planet's surface cannot be seen in visible light due to its opaque atmosphere. Instead, radar mapping has been used to reveal mountains, plains, and large volcanic structures. Despite its brightness in the sky, Venus is a harsh and hostile environment. The atmospheric pressure at the surface is more than 90 times that of Earth's, equivalent to the pressure found nearly a kilometre underwater in Earth's oceans. Understanding Venus provides insight into climate processes, planetary geology, and the divergent evolution of planets that begin with similar conditions. Venus's atmosphere is composed of approximately 96.5% carbon dioxide and 3.5% nitrogen, with trace amounts of other gases such as sulfur dioxide, water vapour, carbon monoxide, and argon. The thick atmosphere extends over 250 kilometers above the surface and contains multiple cloud layers. These clouds are made of sulfuric acid droplets and stretch from roughly 45 to 70 kilometers in altitude. Beneath the clouds, a haze of smaller particles extends closer to the surface. The atmosphere is divided into several temperature and pressure zones. As altitude increases, the temperature and pressure decrease. Near the top, temperatures can fall to -70 degrees Celsius, but deeper down, the heat becomes intense and oppressive. Winds in the upper atmosphere move at incredible speeds, reaching up to 360 kilometers per hour. These super-rotating winds circle the planet much faster than the planet itself rotates. This rapid circulation distributes heat around the planet and contributes to its uniform surface temperature. Studying Venus's atmosphere provides valuable comparisons for understanding Earth's climate and potential future changes due to greenhouse gas accumulation. Because of its dense cloud cover, Venus's surface was long a mystery. Radar imaging from missions such as NASA's Magellan spacecraft has provided detailed maps of the terrain. Venus's surface features broad plains, highland regions, and large volcanic formations. About 80% of the surface is covered by smooth volcanic plains, formed by extensive lava flows. The two main highland areas are Ishtar Terra in the northern hemisphere and Aphrodite Terra near the equator. These regions are comparable in size to continents on Earth and feature complex mountain ranges. One of the most notable surface features is Maxwell Montes, the highest mountain on Venus, rising about 11 kilometers above the average planetary surface level. This elevation surpasses Mount Everest. Venus also has many large circular structures called coronae. These are thought to be caused by upwellings of magma beneath the crust, leading to bulging and fracturing. The relatively low number of impact craters on Venus suggests the surface is geologically young, likely less than 800 million years old, indicating that resurfacing processes, such as volcanic activity, have erased older features. Volcanism plays a major role in shaping Venus's surface. Venus has thousands of volcanic features, including broad shield volcanoes, lava plains, and volcanic domes. Some of the largest volcanoes, such as Matmons and Sifmons, rise several kilometers high and span hundreds of kilometers across. Unlike Earth, there is no clear evidence of plate tectonics on Venus. Instead, heat from the planet's interior appears to be released through widespread volcanic activity. The crust seems to act as a single rigid shell rather than being divided into moving plates. Some studies have found evidence suggesting that Venus may still be volcanically active. Observations from orbit have detected transient hotspots and sulfur dioxide variability in the atmosphere, which could be linked to recent eruptions. The presence of these potential active regions makes Venus one of the most geologically intriguing planets. Understanding its internal dynamics could help scientists better understand the geological evolution of terrestrial planets without plate tectonics. Venus's rotation and orbit are unusual compared to other planets in the solar system. It has a very slow rotation period. One full rotation takes about 243 Earth days. Interestingly, this is longer than its year, which lasts about 225 Earth days. Venus also rotates in the opposite direction to most other planets, a motion called retrograde rotation. This means that if you were standing on the surface, the Sun would appear to rise in the west and set in the east, opposite to Earth's experience. Despite its slow rotation, Venus has relatively consistent temperatures across its surface. This is due to the thick atmosphere and rapid wind circulation that evenly distribute heat. Venus's orbit around the Sun is nearly circular, with a very low eccentricity. It remains at an average distance of about 108 million kilometers from the Sun. Because of its proximity, Venus appears very bright in Earth's sky and is often referred to as the morning star or evening star. These orbital and rotational characteristics contribute to Venus's extreme surface environment and its visibility from Earth. The surface conditions on Venus are among the most extreme in the solar system. Atmospheric pressure at the surface is over 90 times greater than Earth's. This intense pressure would crush most spacecraft or equipment not specially designed to withstand it. The high pressure is a result of the dense carbon dioxide atmosphere and the mass of the overlying air. The surface temperature, consistently around 465 degrees Celsius, is maintained by the thick greenhouse effect. Sunlight passes through the atmosphere and warms the ground, but the outgoing infrared radiation is trapped by carbon dioxide, creating a thermal blanket that prevents cooling. Due to the opacity of the atmosphere, very little sunlight reaches the surface. The lighting conditions are similar to those of a heavily overcast day on Earth, and visibility is limited by the thick haze. These extreme conditions make Venus a challenging place to explore. Only a few spacecraft, primarily from the Soviet Venera program, have successfully landed and transmitted data before being destroyed by heat and pressure. These hostile conditions underscore the contrast between Venus and Earth. Despite their similar sizes and origins, Venus has been explored by numerous missions, providing valuable data on its atmosphere, surface, and overall structure. The earliest missions to Venus were conducted by the Soviet Union. The Venera program, active between 1961 and 1984, sent several probes to the planet. Venera 7 became the first spacecraft to land on another planet and transmit data back to Earth in 1970. Later missions like Venera 13 provided color images and chemical analysis of the surface. NASA's Pioneer Venus project in the late 1970s studied the atmosphere and mapped surface elevations using radar. The most detailed surface mapping came from NASA's Magellan mission, which orbited Venus from 1990 to 1994 and used radar to map over 98% of the surface. The European Space Agency's Venus Express orbited the planet from 2006 to 2014, studying atmospheric composition and circulation. It helped identify signs of potential volcanic activity and tracked long-term climate variations. Japan's Akatsuki mission, launched in 2010, is currently studying Venus's atmosphere and weather patterns. It is the only active mission at Venus as of now. Future missions, such as NASA's Veritas and Da Vinci Plus, are planned to further investigate Venus's geology and atmosphere. Venus provides a powerful example of the greenhouse effect in action. The planet's dense carbon dioxide atmosphere traps heat very effectively. As solar radiation enters the atmosphere, it warms the surface. This surface then emits infrared radiation, but this energy is absorbed and re-radiated by carbon dioxide molecules, preventing it from escaping into space. This runaway greenhouse effect has led to the highest surface temperatures of any planet in the solar system, even though Venus is not the closest to the Sun. In contrast, Earth's atmosphere contains a balance of gases that regulate temperature through a moderate greenhouse effect. Venus shows what can happen when that balance is tipped toward excessive heat retention. By comparing Venus and Earth, scientists gain insights into the long-term impacts of atmospheric composition on planetary climate. This helps improve climate models and predictions on Earth. Understanding Venus's atmosphere also aids in the study of exoplanets, especially those in similar orbits around other stars, and helps define the conditions for planetary habitability. Venus does not have a global magnetic field like Earth's. Instead, it has an induced magnetosphere formed by the interaction between the solar wind and its ionosphere. When charged particles from the Sun encounter Venus's upper atmosphere, they are deflected and create a bow shock, similar to a wave forming in front of a boat. The lack of a strong intrinsic magnetic field means that Venus's atmosphere is more directly exposed to solar wind. Over long periods, this interaction can strip away lighter particles, especially hydrogen and oxygen. Scientists believe that Venus may have once had more water, but the loss of hydrogen to space contributed to its current arid state. The remaining oxygen may have reacted with surface minerals, or escaped the planet entirely. Studying Venus's interaction with the solar wind helps researchers understand atmospheric loss and magnetic shielding. These processes are important for modelling how planets retain their atmospheres and support potential habitability. Venus shows how planetary atmospheres evolve in the absence of protective magnetic fields, offering context for other planets and exoplanets with similar traits. Venus has long been a significant object in human culture and astronomy. It is one of the brightest natural objects in the sky and has been known since ancient times. Because of its proximity to the Sun, Venus appears shortly after sunset or before sunrise, earning it the names morning star and evening star. Early civilizations, including the Babylonians, Mayans, and Greeks, tracked Venus's movements and associated it with gods and goddesses. The planet was often linked to love and beauty due to its brightness, and it played a role in calendars and agricultural timing. Venus's transits across the Sun, rare events that occur in pairs roughly every century, have historically helped astronomers measure the scale of the solar system. Despite centuries of observation, many of Venus's features remained unknown until the age of space exploration. Radar mapping and space missions have transformed our understanding of the planet from a point of light in the sky to a dynamic and complex world. These cultural and scientific perspectives continue to inform how Venus is studied and appreciated in modern astronomy. Venus remains one of the most intriguing planets in the solar system. Its surface conditions are extreme, but they offer clues about planetary evolution, atmospheric science, and the effects of greenhouse warming. Ongoing and future missions will help answer open questions about its geology and possible volcanic activity. As we conclude our study of Venus, we look ahead to the next planet in our journey, Earth. Though familiar, Earth holds its own wonders when seen from a cosmic perspective. Let your thoughts settle like the clouds above Venus, thick and slow-moving, and rest in the knowledge that each world holds lessons about our place in the universe. Earth is the third planet from the Sun, and the only known world to support life. It is unique among the planets in the solar system because of its liquid water, stable atmosphere, and active geology. These combined factors make Earth a dynamic and habitable environment. With a diameter of approximately 12,742 kilometers, Earth is the fifth largest planet. It is classified as a terrestrial planet, meaning it has a solid surface and a layered internal structure. Earth consists of a core, mantle, and crust, which together drive tectonic activity and magnetic field generation. Earth's surface is about 71% covered in water, primarily in the form of oceans. The remaining 29% consists of continents and islands. This balance between land and sea contributes to Earth's ability to regulate temperature and support a diverse range of ecosystems. The atmosphere is composed mostly of nitrogen and oxygen, with smaller amounts of carbon dioxide, water vapor, and other gases. This mix is essential for life as we know it, enabling respiration and moderating the planet's temperature through the greenhouse effect. Understanding Earth's structure, processes and systems helps scientists study climate change, natural hazards, and the conditions required for life elsewhere. Earth's interior is divided into several layers, each with distinct properties. At the center lies the inner core, a solid sphere composed primarily of iron and nickel. It is about 1,220 kilometers in radius and remains solid despite temperatures reaching up to 5,700 degrees Celsius due to the immense pressure. Surrounding the inner core is the outer core, a fluid layer of molten metal that generates Earth's magnetic field through convection and rotation. The movement of this electrically conductive fluid acts like a dynamo, producing the geomagnetic field that shields the planet from solar and cosmic radiation. Above the outer core is the mantle, which extends to a depth of about 2,900 kilometers. The mantle is composed mainly of silicate rocks and behaves as a solid over short timescales, but can flow slowly over long periods. This slow movement drives tectonic processes at the surface. The outermost layer is the crust, which varies in thickness from about 5 kilometers under oceans to up to 70 kilometers under continents. The crust is broken into tectonic plates that move due to mantle convection, leading to earthquakes, volcanic activity, and mountain formation. Studying Earth's internal layers helps geologists understand the mechanisms behind plate tectonics and the thermal history of the planet. The theory of plate tectonics explains how Earth's surface is shaped by the movement of large plates of the lithosphere. These plates float on the semi-fluid asthenosphere beneath them, driven by convection currents in the mantle. As plates move, they interact at boundaries in different ways. They may diverge, converge, or slide past each other. At divergent boundaries, plates move apart, allowing magma to rise and create new crust. This process occurs at mid-ocean ridges and is responsible for seafloor spreading. At convergent boundaries, plates collide, leading to subduction or mountain building, depending on the nature of the colliding plates. Subduction zones, where one plate is forced beneath another, are sites of intense geological activity, including volcanic eruptions and earthquakes. Transform boundaries, where plates slide past one another, also produce frequent seismic events. The movement of tectonic plates constantly reshapes the surface of the Earth. Mountain ranges, ocean trenches, and earthquake zones are all consequences of this dynamic process. Plate tectonics also plays a role in the long-term carbon cycle, regulating atmospheric carbon dioxide through weathering and volcanic emissions. This connection helps maintain Earth's climate over geological timescales. Earth's atmosphere is a complex mixture of gases that protects life and regulates the planet's climate. The atmosphere consists primarily of nitrogen, about 78%, and oxygen, about 21%, with trace gases such as argon, carbon dioxide, and water vapor making up the remainder. These gases are held close to Earth's surface by gravity and extend upward for hundreds of kilometers. The atmosphere is divided into several layers: the troposphere, stratosphere, mesosphere, thermosphere, and exosphere. Weather occurs in the troposphere, the lowest layer, where temperature decreases with altitude. The stratosphere contains the ozone layer, which absorbs harmful ultraviolet radiation from the sun. Greenhouse gases like carbon dioxide, methane, and water vapor trap heat from the sun, keeping Earth's surface warm enough to sustain life. This natural greenhouse effect is essential, but human activities have increased the concentration of these gases, intensifying global warming. The climate system is influenced by atmospheric circulation, ocean currents, solar radiation, and surface characteristics. These factors interact to create diverse climate zones, from tropical rainforests to polar ice caps. Understanding the atmosphere helps scientists predict weather patterns, study climate change, and monitor air quality, all of which are crucial for sustaining life on Earth. The hydrosphere includes all of Earth's water in liquid, solid, and vapor forms. Oceans are the most prominent part of the hydrosphere, covering about 71% of the planet's surface. They contain roughly 97% of Earth's water and play a key role in regulating climate and supporting marine ecosystems. The remaining water is found in glaciers, ice caps, rivers, lakes, groundwater, and the atmosphere. Although fresh water makes up only about 2.5% of Earth's total water, it is essential for drinking, agriculture, and sanitation. The water cycle describes how water moves through the environment. Processes such as evaporation, condensation, precipitation, and runoff circulate water between the atmosphere, oceans, and land. This continuous movement supports life and influences weather patterns. Oceans absorb and store large amounts of solar energy. Currents transport heat from equatorial regions toward the poles, helping balance global temperatures. The interaction between the atmosphere and oceans also drives phenomena like El Niño and La Niña, which affect weather worldwide. The hydrosphere interacts closely with the atmosphere, biosphere, and geosphere, making it a vital component of Earth's integrated systems. The biosphere encompasses all living organisms on Earth and their interactions with the physical environment. Life exists in a wide range of habitats, from deep ocean vents to high mountain peaks. Earth's biosphere includes forests, grasslands, deserts, tundras, and coral reefs, each supporting unique ecosystems. Biodiversity is a measure of the variety of life, from genetic diversity within species to the range of species and ecosystems. High biodiversity contributes to ecosystem resilience and stability. Life depends on key environmental conditions: liquid water, a stable temperature range, energy from the sun, and a suitable chemical environment. These conditions have remained relatively stable for much of Earth's history, allowing complex life to evolve. Photosynthesis, carried out by plants and algae, converts sunlight into chemical energy and produces oxygen as a byproduct. This process is the foundation of most food chains and helps regulate atmospheric carbon dioxide. The biosphere interacts with the atmosphere, hydrosphere, and geosphere. For example, forests influence climate by absorbing carbon dioxide, and soil organisms affect nutrient cycling. Understanding the biosphere is essential for conservation efforts, agriculture, and addressing the impacts of human activity on natural systems. Earth's magnetic field is generated by the movement of molten metal in the outer core. This field extends from the planet's interior into space, forming the magnetosphere. It deflects charged particles from the solar wind, protecting the atmosphere from erosion and reducing the amount of radiation that reaches the surface. The magnetic field is not static. It shifts and varies in intensity over time. Occasionally, the magnetic poles reverse, a process that occurs irregularly on geological timescales. These reversals leave a record in the orientation of minerals in ancient rocks. The magnetosphere also influences space weather, affecting satellite communications, navigation systems, and electrical grids. Auroras, visible near the poles, are caused by solar particles interacting with Earth's magnetic field and atmosphere. Monitoring the magnetic field helps scientists study Earth's interior and its interactions with the solar environment. Earth's moon is its only natural satellite and plays a significant role in shaping the planet's environment. The moon is about 1/4 the size of Earth and orbits at an average distance of approximately 384,400 kilometers. It has a diameter of about 3,474 kilometers and is composed mainly of silicate rock. The Moon's gravitational pull causes tides in Earth's oceans. These tidal forces influence coastal ecosystems, marine life, and the rotation of the planet. The Moon also stabilizes Earth's axial tilt, which contributes to a relatively stable climate over long timescales. The lunar surface is covered with craters, plains, and mountains. It lacks an atmosphere, so temperatures vary widely between day and night. The Moon's surface preserves a record of impacts and geological activity dating back billions of years. The Moon is thought to have formed after a collision between Earth and a Mars-sized body early in the solar system's history. The resulting debris coalesced to form the Moon. Studying the Moon provides insights into the early solar system and the processes that shaped Earth. It also serves as a stepping stone for future space exploration. Earth occupies a special position in the solar system's habitable zone, the region around the Sun where temperatures allow liquid water to exist. This location, combined with a protective atmosphere and magnetic field, makes Earth uniquely suited for life. Its orbital characteristics and axial tilt produce seasons, while its rotation creates a day-night cycle that influences biological rhythms. Earth's interactions with other bodies in the solar system are also important. The gravitational pull of the Moon and Sun affects tides and orbital dynamics. Impacts from asteroids and comets have influenced Earth's geological and biological history. The study of Earth as a planetary system, including its atmosphere, oceans, crust, and biosphere, provides a model for understanding other planets. Scientists use Earth-based observations to interpret data from space missions and to assess the potential habitability of exoplanets. As space exploration advances, Earth serves as a reference point for identifying planets that might support life elsewhere in the universe. Mars is the fourth planet from the Sun and the second smallest in the solar system. Often referred to as the red planet, its surface is coated in iron oxide, giving it a distinct reddish hue. Mars has long captured human curiosity, both for its unique geological features and the possibility that it once supported life. The planet has a diameter of about 6,779 kilometers, making it roughly half the size of Earth. It is a terrestrial planet with a thin atmosphere, cold climate, and a rocky surface marked by craters, valleys, and volcanoes. Mars has two small, irregularly shaped moons, Phobos and Deimos. These moons are thought to be captured asteroids from the asteroid belt and contribute to the planet's dynamic gravitational environment. Scientists have studied Mars extensively using orbiters, landers, and rovers. Missions such as Viking, Spirit, Opportunity, Curiosity, and Perseverance have provided valuable data about the planet's surface composition, climate history, and potential for habitability. Mars is of particular interest in planetary science due to its similarities and differences with Earth, especially regarding water, atmosphere, and geology. Mars has some of the most striking surface features in the solar system. One of the most prominent is Olympus Mons, the tallest known volcano and mountain in the solar system. It stands approximately 22 kilometers high, about 2.5 times the height of Mount Everest. Olympus Mons is a shield volcano formed by repeated lava flows over long periods. Another major feature is Valles Marineris, a vast canyon system that stretches over 4,000 kilometers and is up to 7 kilometers deep. This canyon dwarfs Earth's Grand Canyon and is thought to have formed due to tectonic forces that cracked the crust as the planet cooled. Mars also has extensive impact craters, such as Hellas Planitia, one of the largest impact basins in the solar system. These craters reveal past impacts. The surface of Mars includes both ancient highlands and relatively smooth lowlands. The northern hemisphere contains large plains that may have been shaped by ancient oceans, while the southern hemisphere is heavily cratered and older. Wind erosion, dust storms, and occasional frost also contribute to ongoing surface changes. Although the planet is geologically inactive compared to Earth, its landscape still shows signs of past dynamism. Mars has a thin atmosphere composed mostly of carbon dioxide, with small amounts of nitrogen, argon, and trace gases. Unlike Earth's atmosphere, it lacks sufficient pressure to support liquid water on the surface under current conditions. The surface pressure on Mars is less than 1% of Earth's, averaging about 610 pascals. This low pressure contributes to rapid evaporation or sublimation of water ice, and challenges for human exploration. The planet's atmosphere is not dense enough to provide significant insulation, so surface temperatures can fluctuate dramatically. Daytime temperatures near the equator may reach up to 20 degrees Celsius, while nighttime temperatures can drop to -100 degrees Celsius or lower. Seasonal variations occur due to Mars' axial tilt of about 25 degrees, similar to Earth's. This tilt results in Martian seasons, which are longer than Earth's due to the planet's slower orbit around the Sun. Mars experiences global dust storms that can last for weeks or months and envelop the entire planet. These storms are driven by solar heating and atmospheric circulation, and they significantly influence surface conditions and visibility for spacecraft. Understanding the atmosphere informs scientists about Mars' climate history and water loss. One of the most intriguing aspects of Mars is its history with water. Today, liquid water cannot exist for long on the surface due to the low pressure and cold temperatures. However, there is substantial evidence that Mars once had flowing water and possibly standing bodies of water like rivers, lakes, and even oceans. Features such as dry riverbeds, deltas, and valley networks suggest that liquid water shaped the Martian surface billions of years ago. These formations point to a period when the climate was warmer and the atmosphere thicker. In the polar regions, Mars has large ice caps composed of water ice and frozen carbon dioxide. These caps grow and shrink with the seasons and contain layered deposits that record climate changes over time. Additionally, orbital observations and rover data have detected hydrated minerals and sedimentary rocks. These materials form in the presence of water and provide clues to the chemical environment of ancient Mars. Subsurface ice has also been discovered in various locations, and there is some evidence suggesting that briny liquid water may still exist underground in isolated pockets. Studying water on Mars is essential for understanding its geological history, the potential for past life, and the feasibility of future human missions. Mars has been the focus of numerous robotic exploration missions aimed at understanding its environment and potential habitability. The first successful missions to Mars were orbiters like Mariner 9 in 1971, which provided the first detailed maps of the Martian surface. Viking 1 and 2 followed with landers in 1976, conducting biological experiments and capturing panoramic images. In the late 1990s and 2000s, missions such as Mars Pathfinder and the twin rovers Spirit and Opportunity brought new insights. These rovers analyzed soil and rocks, revealing more about Mars' watery past. The Curiosity rover, which landed in 2012, has been exploring Gale Crater. it has found evidence of ancient lakes and organic molecules, contributing to the understanding of potentially habitable environments. Most recently, the Perseverance rover arrived in 2021. It is studying the geology of Jezero crater and collecting rock samples for future return to Earth. Perseverance is also accompanied by Ingenuity, a small helicopter that achieved the first powered flight on another planet. These missions represent decades of progress in robotic exploration and serve as a foundation for eventual crewed missions to Mars. Mars exhibits evidence of past volcanic and tectonic activity, though it is currently considered geologically inactive. The planet's surface is dotted with volcanic features, including lava plains, volcanic cones, and extensive basaltic flows. Olympus Mons, as mentioned earlier, is the largest volcano in the solar system, but it is not the only one. The Tharsis region has other large volcanoes. These volcanoes are thought to have formed during a time of active mantle convection, when hot material from the planet's interior rose through the crust. The lack of plate tectonics on Mars allowed lava to erupt in the same location repeatedly, building up massive structures over time. Unlike Earth, Mars does not have distinct tectonic plates that shift and interact. However, features such as fault lines, rift valleys, and surface fractures suggest that the crust has undergone stress and deformation. Seismic activity, or Marsquakes, has been detected by the InSight lander, which deployed a sensitive seismometer to monitor the Martian interior. These quakes indicate that the planet still retains some internal heat and structural movement. Studying Martian geology helps scientists understand planetary evolution and the conditions that might support or hinder the development of life. The question of whether life ever existed on Mars is one of the most compelling in planetary science. Mars today is a cold, dry, and radiation-exposed environment, but in the distant past it may have had conditions suitable for microbial life. Evidence of ancient lakes, rivers, and potentially habitable environments has led scientists to search for signs of past or present life. The Viking landers in the 1970s conducted experiments to detect biological activity in the Martian soil. The results were inconclusive and continue to be debated. More recent missions have focused on detecting organic molecules and assessing environmental conditions that could support life. Curiosity and Perseverance have both discovered organic compounds in Martian rocks, although these molecules can also be produced through non-biological processes. The presence of these compounds does not confirm life, but does suggest that the chemical building blocks were present. Future missions, including sample return efforts, aim to analyze Martian soil and rock in greater detail. These studies will help determine whether Mars ever hosted microbial organisms or still harbors life in protected environments underground. While no definitive evidence of life has been found, the ongoing exploration of Mars continues to shape our understanding of life's potential beyond Earth. Mars has two small moons named Phobos and Deimos. These irregularly shaped bodies are thought to be captured asteroids from the asteroid belt. Phobos, the larger of the two, orbits very close to Mars at a distance of about 6,000 kilometers. It is gradually spiraling inward due to tidal forces and is expected to either crash into Mars or break apart into a ring in about 50 million years. Deimos is smaller and orbits much farther away, following a more stable trajectory. Both moons have low gravity, heavily cratered surfaces, and are composed of dark, carbon-rich rock. The origin of Phobos and Deimos is not fully understood. Some theories suggest they formed from debris ejected by an ancient impact on Mars, while others propose that they are captured objects from the outer solar system. These moons are of interest to scientists because studying them can reveal information about the early solar system and planetary satellite formation. Future missions may visit or even land on these moons as part of broader efforts to explore the Martian system. Phobos and Deimos, though small, add to the complexity and intrigue of Mars as a planetary environment. Human exploration of Mars has long been a goal of space agencies and researchers. The challenges are significant, but progress continues toward eventual crewed missions. One major challenge is the travel distance. Depending on the alignment of the planets, a round-trip journey to Mars could take more than a year. This requires durable spacecraft, life support systems, and protection from cosmic radiation. NASA, the European Space Agency, and private companies such as SpaceX are actively developing technologies for crewed missions. These include propulsion systems, surface habitats, and plans for landing and returning safely. In situ resource utilization, ISRU, is another area of focus. This involves using Martian resources, such as extracting water from ice or producing oxygen from the atmosphere, to support long-term stays. Human missions to Mars could offer insights into the planet's history and geology, and help determine its potential for supporting life. These missions also improve planetary exploration tech. As planning continues, robotic missions will continue to pave the way, collecting data and testing systems that will support future astronauts. The dream of walking on Mars may become a reality in the coming decades. Jupiter is the fifth planet from the Sun and the largest in the solar system. It is a gas giant composed primarily of hydrogen and helium, with no solid surface like Earth or Mars. Its immense size, powerful magnetic field, and complex atmosphere make it a subject of great interest in planetary science. The planet has a diameter of about 139,820 kilometers, more than 11 times that of Earth. Its mass is over 300 times that of Earth, and its volume is large enough to contain more than 1,300 Earths. Jupiter's strong gravitational influence shapes the orbits of many other objects in the solar system, including asteroids and comets. Its position and mass play a protective role, helping to deflect debris that might otherwise impact the inner planets. The planet rotates rapidly, completing one rotation approximately every 10 hours. This fast rotation contributes to its distinctive shape, an oblate spheroid, with a noticeable bulge at the equator. Despite being a gas giant, Jupiter may have a solid core composed of heavier elements. However, its exact internal structure remains a topic of scientific research and ongoing observation. Jupiter's atmosphere is composed mostly of hydrogen and helium, with trace amounts of methane, ammonia, water vapor, and other compounds. These gases form distinct layers and contribute to the planet's banded appearance. The outer atmosphere is characterized by alternating bands of lighter and darker clouds, known as zones and belts. These bands are driven by powerful jet streams that flow in opposite directions, creating turbulence and complex weather patterns. One of the most iconic features in Jupiter's atmosphere is the Great Red Spot. This is a persistent high-pressure storm system located in the southern hemisphere. It has been observed for over 350 years and is large enough to encompass the Earth. The atmosphere is layered, with ammonia clouds at higher altitudes and deeper layers containing ammonium hydrosulfide and water clouds. The exact composition and dynamics of these layers are still being studied using both ground-based telescopes and spacecraft observations. Jupiter experiences strong auroras near its poles, caused by interactions between the magnetic field and charged particles from the solar wind and its moons. These auroras are more powerful than those found on Earth. The overall temperature in the upper atmosphere is extremely cold, around -145 degrees Celsius, but the deeper layers are warmer due to internal heat generated by the planet itself. Jupiter has the strongest magnetic field of any planet in the solar system. This magnetic field is generated by the movement of metallic hydrogen in the planet's interior. It extends millions of kilometers into space and forms a vast magnetosphere. The magnetosphere traps charged particles from the solar wind and the volcanic emissions of Jupiter's moon Io. These particles create intense radiation belts around the planet, which pose significant challenges for spacecraft and would be hazardous to human health. The magnetic field also interacts with Jupiter's moons, particularly Io, generating electric currents that contribute to auroras and radio emissions. Within the magnetosphere, particles move along magnetic field lines and can become accelerated to high energies. These energetic particles create bright auroras and contribute to heating the upper atmosphere. Jupiter's magnetosphere is asymmetric and shaped by the solar wind. On the side facing the Sun, it is compressed, while the opposite side forms a long tail that stretches far beyond Saturn's orbit. Understanding Jupiter's magnetic environment provides insights into the planet's internal structure, as well as comparative studies with Earth's magnetic field and space weather phenomena in general. Jupiter's internal structure is inferred from models and spacecraft measurements. Although it lacks a solid surface, the planet is believed to have a dense core made of rock, metal, and possibly ice. Above the core is a thick layer of metallic hydrogen, where hydrogen atoms are compressed into a liquid metallic state due to extreme pressure. This region is responsible for generating the planet's magnetic field. Surrounding the metallic hydrogen layer is a vast region of liquid molecular hydrogen and helium. As one moves outward, the density and pressure decrease, transitioning gradually into the upper atmosphere. The transition between these layers is not sharply defined, and there may be regions where materials mix or flow in complex patterns. Jupiter's rapid rotation also influences internal circulation and helps maintain the banded appearance of the atmosphere. The planet emits more heat than it receives from the Sun. This excess heat comes from the gradual contraction of the planet and the release of gravitational energy, a process known as Kelvin-Helmholtz contraction. Studying Jupiter's internal composition helps scientists understand how gas giants form and evolve, both in our solar system and in planetary systems around other stars. Jupiter has at least 95 known moons, but the four largest are called the Galilean moons: Io, Europa, Ganymede, and Callisto. These were first observed by Galileo Galilei in 1610 and are among the most fascinating objects in the solar system. Io is the most volcanically active body in the solar system, with hundreds of active volcanoes. Its surface is constantly reshaped by lava flows and sulfur deposits. Volcanic activity on Io is driven by tidal forces from Jupiter's gravity. Europa is of particular interest because it may harbour a subsurface ocean beneath its icy crust. This ocean could contain more than twice the volume of Earth's oceans and is considered one of the most promising places to search for extraterrestrial life. Ganymede is the largest moon in the solar system and even bigger than the planet Mercury. It has its own magnetic field, a feature unique among moons, and shows evidence of a layered interior with ice, rock, and possibly a subsurface ocean. Callisto, the outermost of the Galilean moons, is heavily cratered and geologically inactive. Its ancient surface preserves a record of impacts and conditions from the early solar system. These moons are being studied by missions such as the European Space Agency's Jupiter Icy Moons Explorer, JUICE, and NASA's Europa Clipper, both of which aim to explore their potential habitability and internal structures. Jupiter plays a critical role in the structure and evolution of the solar system. Its strong gravitational field influences the orbits of planets, asteroids, and comets. The planet helps shape the asteroid belt by maintaining gaps known as Kirkwood gaps, where gravitational resonances with Jupiter prevent stable orbits. These resonances also contribute to the formation of asteroid families and clusters. Jupiter's gravity is believed to have played a role in the migration of the giant planets during the early history of the solar system. This migration could have influenced the distribution of water and other materials essential for life on Earth. The planet is sometimes referred to as a cosmic vacuum cleaner because it captures or deflects incoming comets and asteroids, reducing the likelihood of collisions with the inner planets. However, in some cases, Jupiter's gravity can redirect objects toward the inner solar system. By studying Jupiter's interactions with smaller bodies, scientists gain insights into planetary dynamics, orbital mechanics, and the processes that govern long-term solar system evolution. Jupiter's role as a gravitational anchor helps maintain the stability of the planetary system over billions of years. Jupiter has been known since ancient times and has played a significant role in mythology and astronomy. In Roman mythology, Jupiter was the king of the gods, corresponding to Zeus in Greek mythology. The planet's brightness and regular motion made it an important object for early skywatchers. Ancient Babylonians and Chinese astronomers recorded observations of Jupiter, and its position was used to track time and predict celestial events. Galileo's discovery of the 4 largest moons provided strong evidence that not all celestial bodies revolve around Earth. This finding was crucial in advancing the heliocentric model of the solar system. Jupiter's moons also influenced the development of scientific methods and instrumentation. The observation of their motions led to improvements in timekeeping and navigational techniques. Today, Jupiter continues to inspire scientific inquiry and public interest. Images from telescopes and spacecraft reveal its dynamic atmosphere, complex moon system, and powerful magnetosphere. The ongoing exploration of Jupiter bridges the gap between ancient curiosity and modern science, offering both a sense of historical continuity and a path toward future discoveries. Jupiter has been visited by several spacecraft, each contributing to our understanding of the planet and its environment. The Pioneer 10 and 11 missions were the first to fly by Jupiter in the early 1970s. They provided the first close-up images and data on the magnetic field and radiation belts. Voyager 1 and 2 continued the exploration in 1979, capturing detailed images of the atmosphere, rings and moons. These missions revealed the volcanic activity on Io and the icy surface of Europa. The Galileo spacecraft, launched in 1989, entered orbit around Jupiter in 1995 and studied the planet and its moons for more than 7 years. It deployed a probe into the atmosphere and provided extensive data on the Galilean moons. More recently, the Juno mission, launched in 2011, entered a polar orbit around Jupiter in 2016. Juno is studying the planet's magnetic field, gravity, atmosphere, and internal structure. Its data have led to revisions in models of how gas giants form and evolve. Future missions such as JUICE and Europa Clipper aim to continue this work by focusing on the icy moons and their potential to support life. These missions will carry advanced instruments to analyze surface chemistry, magnetic environments, and possible subsurface oceans. Although Jupiter is best known for its size and moons, it also has a faint ring system. These rings are composed mainly of dust particles ejected from some of its small inner moons. The ring system was discovered in 1979 by the Voyager 1 spacecraft. It consists of three main components: the halo ring, the main ring, and the gossamer rings. The halo ring is the innermost and is thick and diffuse. The main ring is relatively narrow and brighter, while the gossamer rings are faint and extend farther from the planet. Unlike Saturn's icy rings, Jupiter's rings are dark and made of microscopic dust particles. These particles are thought to be continuously replenished by micrometeoroid impacts on the small moons. The existence of these rings highlights the dynamic processes at work in Jupiter's environment. The planet's rapid rotation and strong gravity contribute to the stability and behavior of the ring system. In addition to the Galilean moons, Jupiter has dozens of smaller moons, many of which are irregular and captured objects. These moons vary in size, shape, and composition, and provide clues about the planet's gravitational influence and capture history. Jupiter is a planet of extremes and complexity. Its immense size, powerful magnetic field, diverse moon system, and dynamic atmosphere make it a key subject for planetary science. From its turbulent clouds to its deep interior, every layer of Jupiter presents an opportunity to study the processes that shape gas giants. Its gravitational influence helps maintain the structure of the solar system and may have helped protect Earth from excessive impacts. The exploration of Jupiter has expanded our understanding of planetary formation, magnetic environments, and the potential for life on icy moons. As we continue to send missions to study Jupiter and its satellites, new data will refine our models and reveal more about the origin and evolution of the solar system. Jupiter's deep pulse, visible in its storms, fields, and orbiting companions, offers a window into the workings of planets near and far. Its study not only enriches our scientific knowledge, but also continues a legacy of curiosity that spans centuries. Saturn is the sixth planet from the Sun, and the second largest in the solar system. Like Jupiter, it is a gas giant primarily composed of hydrogen and helium. Saturn is most famous for its striking ring system, which is the most extensive and complex among all the planets. The planet has an equatorial diameter of approximately 120,500 kilometers, making it about 9.5 times wider than Earth. Despite its size, Saturn is the least dense planet in the solar system. Its overall density is lower than that of water, meaning it would float in a sufficiently large body of water. Saturn completes one rotation in about 10.7 hours, contributing to its flattened shape at the poles and bulging at the equator. Its axial tilt of 26.7 degrees causes the planet to experience seasons, much like Earth, though each season lasts over 7 Earth years. The upper atmosphere of Saturn exhibits a banded structure similar to Jupiter's, with alternating zones and belts. These bands are driven by high-speed winds that can reach speeds of over 1,800 kilometers per hour near the equator. Saturn's atmosphere is composed mostly of hydrogen, with smaller amounts of helium, methane, ammonia, and other trace gases. The outermost layer is made up of thick clouds that form bands around the planet, similar in appearance to Jupiter's cloud structures. The clouds are organized into different layers based on temperature and chemical composition. The upper layers consist mainly of ammonia ice, while deeper layers may contain ammonium hydrosulfide and water ice clouds. These layers are not directly visible but are inferred from data collected by spacecraft and telescopes. One of Saturn's most unusual atmospheric features is the persistent hexagon-shaped jet stream located at its north pole. This hexagon spans roughly 30,000 kilometers across and rotates with the planet. Its formation remains a topic of research, but it is believed to be caused by stable atmospheric flows at specific latitudes. Saturn also exhibits large, long-lasting storms. One such storm, known as the Great White Spot, appears approximately every 30 Earth years. These storms are massive enough to encircle the entire planet and are driven by heat from the planet's interior and atmospheric dynamics. Lightning on Saturn has been observed by spacecraft such as Cassini. These electrical discharges are associated with deep convective clouds and can be more powerful than those found on Earth. Saturn's rings are its most prominent and distinguishing feature. They're composed mainly of water ice particles, with traces of rocky material and dust. The rings extend from about 7,000 kilometers to over 80,000 kilometers above Saturn's equator, but are typically only about 10 meters thick. The ring system is divided into several main sections, labeled alphabetically in the order of their discovery: D, C, B, A, F, G, and E rings. The A and B rings are the most visible and are separated by the Cassini division, a dark gap caused by gravitational interactions with Saturn's moon Mimas. The particles in Saturn's rings range in size from tiny grains to objects several meters across. These particles orbit Saturn independently, creating patterns of density waves and gaps due to gravitational influences from nearby moons and resonance effects. The rings are thought to be relatively young in astronomical terms, possibly less than 100 million years old. Their origin is uncertain, but they may have formed from the remnants of a destroyed moon or comet that came too close to the planet. Observations from missions such as Cassini have revealed fine details in the rings, including transient features like spokes, which are believed to be caused by electromagnetic interactions between the ring particles and Saturn's magnetic field. Saturn's internal structure consists of several distinct layers. The outermost region is a thick envelope of hydrogen and helium. Beneath this lies a layer of metallic hydrogen, which conducts electricity and generates Saturn's magnetic field. At the core there is likely a dense mixture of rock and ice. The total mass of Saturn's core is estimated to be between 10 and 20 times the mass of Earth. This core is surrounded by a layer of metallic hydrogen, which transitions to molecular hydrogen further outward. The high pressure in the interior compresses hydrogen into a metallic state, which behaves like an electrical conductor. Saturn emits more energy than it receives from the Sun, due to residual heat from its formation and ongoing gravitational compression. This heat drives atmospheric convection and contributes to the planet's weather patterns. Saturn's magnetic field is symmetric and aligned closely with its rotation axis. It is weaker than Jupiter's, but still strong enough to trap charged particles in radiation belts and influence the behavior of nearby moons and the ring system. The magnetosphere of Saturn extends hundreds of thousands of kilometers into space and interacts with the solar wind, producing auroras near the poles. These auroras are visible in ultraviolet wavelengths and have been imaged by orbiting spacecraft. Saturn has a large and diverse system of moons, with more than 140 confirmed natural satellites. These moons vary in size, composition, and geological activity. The largest moon, Titan, is larger than the planet Mercury and has a thick nitrogen-rich atmosphere. It is the only moon in the solar system with a dense atmosphere and surface liquid in the form of methane and ethane lakes. Titan's surface features include dunes, rivers, and possible cryovolcanoes. Another notable moon is Enceladus, a small icy satellite that exhibits geysers of water vapor and organic compounds from fractures near its south pole. These plumes suggest the presence of a subsurface ocean, making Enceladus a target of interest in the search for extraterrestrial life. Other moons of Saturn include Rhea, Iapetus, Dione, Tethys, and Mimas. Each has unique surface characteristics such as impact craters, ridges, and canyons. Some of these moons may also have subsurface oceans. The gravitational interactions between Saturn and its moons play a role in shaping the ring system and maintaining orbital resonances. These interactions also generate tidal forces that affect the geological activity of the moons. The study of Saturn's moons provides valuable information about planetary formation, icy bodies, and the conditions necessary for habitability in the outer solar system. Several spacecraft have visited Saturn, greatly expanding our knowledge of the planet and its moons. The Pioneer 11 mission was the first spacecraft to fly by Saturn in 1979. It provided preliminary data on the planet's magnetic field, atmosphere, and rings. Voyager 1 and 2 followed in the early 1980s, capturing detailed images of Saturn's rings and moons. These missions discovered new ring structures and provided the first close-up views of Titan. The most extensive exploration came from the Cassini mission, a joint project by NASA, ESA, and the Italian Space Agency. Launched in 1997, Cassini arrived at Saturn in 2004 and orbited the planet for more than 13 years. It conducted flybys of Titan and other moons, studied the ring system in detail, and deployed the Huygens probe, which landed on Titan in 2005. Cassini's data provided insights into Saturn's internal structure, seasonal changes, and magnetic field. Its observations of Enceladus's plumes and Titan's atmosphere have been crucial in astrobiological research. The mission concluded in 2017 with a planned descent into Saturn's atmosphere, a maneuver designed to prevent potential contamination of moons that might support life. Future missions to Saturn may focus on detailed exploration of Titan and Enceladus, using advanced instruments to study their subsurface environments. Saturn plays a significant role in the dynamics of the solar system. Its large mass and gravitational influence affect the orbits of nearby asteroids and comets, contributing to the overall structure of the outer solar system. Like Jupiter, Saturn may act as a gravitational shield, deflecting or capturing objects that might otherwise impact the inner planets. This protective role has implications for the long-term stability of the solar system and the development of life on Earth. Saturn is located within the region of the solar system known as the outer planets. These planets are composed primarily of gases and ices, and contrast with the rocky terrestrial planets of the inner solar system. The study of Saturn and its surroundings helps scientists understand how planetary systems form and evolve. Its complex interactions with moons, rings, and the solar wind offer a model for examining similar systems around other stars. Saturn's axis tilt and resulting seasons provide a natural laboratory for studying long-term atmospheric dynamics. Observations of seasonal changes in cloud patterns, ring brightness, and polar phenomena help refine climate models used for both Earth and other planets. Research on Saturn also informs our understanding of gas giant exoplanets, many of which share characteristics with Saturn but exist under different stellar conditions. Saturn's rotation is rapid, completing one full spin in about 10.7 Earth hours. This high rotation rate contributes to the planet's oblate shape, with a noticeable bulge at the equator. Determining Saturn's exact rotation period is difficult due to the lack of a solid surface and variations in magnetic field measurements. The planet's outer atmosphere rotates at slightly different speeds depending on latitude, a phenomenon known as differential rotation. Saturn's magnetosphere is generated by the movement of conducting material in its interior. It is large enough to encompass the planet's rings and many of its moons. The magnetosphere interacts with the solar wind, creating a bow shock and magnetotail similar to Earth's magnetic environment. Within this region, charged particles are trapped in radiation belts and can influence the behavior of the rings and moons. Saturn's magnetic field also produces auroras near its poles, which are visible in ultraviolet light. The auroras are influenced by solar activity and internal processes within the magnetosphere. These displays help researchers study the dynamics of planetary magnetic environments and their responses to external stimuli. Cassini's measurements of the magnetic field and charged particle populations have contributed significantly to the understanding of Saturn's magnetosphere and its interactions with the solar wind and planetary atmosphere. Saturn is a complex and captivating planet, distinguished by its rings, moons, and dynamic atmospheric systems. Its size, low density, and rapid rotation make it unique among the planets. The planet's atmospheric structure, magnetic field, and seasonal variations offer important clues about the behavior of gas giants. Its diverse moon system, especially Titan and Enceladus, provides opportunities for exploring conditions that might support life. The ring system, while visually striking, also serves as a dynamic laboratory for studying orbital mechanics, particle interactions, and the influence of gravitational forces. Saturn's role in shaping the architecture of the solar system and its similarity to many known exoplanets underscore its scientific importance. Ongoing research and future missions will continue to explore Saturn's mysteries, refining our understanding of planetary systems both within and beyond our own. As a subject of exploration, Saturn inspires curiosity and provides a window into the processes that govern the behavior of large gaseous planets. Its study contributes to the broader quest to understand the origins and evolution of our cosmic neighborhood. Additional observations continue to be analyzed by researchers around the world. The data collected from past missions, especially Cassini, is still yielding new insights as scientists reprocess and compare measurements with recent models. As we look toward the future, Saturn remains a focal point for questions about planetary atmospheres, moon geology, and the long-term evolution of gas giants. It is a subject that connects astronomy, planetary science, and astrobiology. In this chapter, we've taken a closer look at Saturn through a scientific lens while maintaining a gentle, sleep-friendly tone. Whether you're curious about its rings or interested in its many moons, Saturn offers a broad spectrum of mysteries that continue to inspire discovery. With this, we gently conclude our visit to Saturn. Our next stop will take us even farther from the Sun, to a planet known for its unique tilt and pale blue glow, Uranus. Uranus is the seventh planet from the Sun and one of the least understood among the major planets in our solar system. Located at an average distance of approximately 2.87 billion kilometers, 1.78 billion miles, from the Sun, Uranus is classified as an ice giant due to its composition and internal structure. It is slightly smaller than Neptune but similar in many characteristics, including its temperature, atmospheric content, and faint ring system. The most notable feature of Uranus is its extreme axial tilt. The planet is tilted at about 98 degrees, meaning it essentially rolls along its orbital path rather than spinning upright like most other planets. This unique orientation causes each pole to experience decades-long periods of sunlight, followed by equally long stretches of darkness. Scientists believe that this tilt was the result of a massive collision early in Uranus's formation, possibly with an Earth-sized object. With a diameter of about 50,724 kilometers, 31,518 miles, Uranus is the third largest planet by diameter in the solar system. However, its mass ranks it as the fourth most massive after Jupiter, Saturn and Neptune. Its relatively low density suggests that it contains a high proportion of lighter elements and ices. The atmosphere of Uranus is primarily composed of hydrogen, about 83%, and helium, 15%, with a small amount of methane, 2%. It is this methane that gives the planet its pale cyan colour. Methane in the upper atmosphere absorbs red light and reflects blue-green wavelengths. The atmosphere also contains trace amounts of water vapour and other hydrocarbons such as ethane and acetylene. Beneath the upper cloud layer, Uranus's interior transitions gradually into a thick, icy mantle composed of water, ammonia, and methane ices. Unlike gas giants like Jupiter and Saturn, which have clearly defined layers, Uranus's internal structure appears more fluid and poorly differentiated. Deeper into the planet, pressures and temperatures increase dramatically, potentially forming exotic states of matter such as supersonic water, a form of ice where hydrogen ions move freely within an oxygen lattice. At the core, there is likely a rocky centre that may be about half the size of Earth. This core is surrounded by the thick mantle of ices mentioned earlier. Overall, Uranus's internal heat is minimal. It emits very little heat into space, far less than other giant planets. The reason for this low thermal emission is still not fully understood. Uranus also exhibits a highly unusual magnetic field. Unlike Earth's magnetic field, which is aligned closely with its rotational axis, Uranus's magnetic field is tilted about 59 degrees from its axis and is significantly offset from the planet's centre. This causes the magnetic field to wobble as the planet rotates, creating a magnetosphere with complex and changing boundaries. The field is believed to be generated in a layer of ionized water, ammonia, and methane deep within the planet's interior. The rotation period of Uranus is relatively short. It completes one full rotation approximately every 17.2 hours. However, because of its axial tilt, the concept of a day on Uranus is more complicated when observed from the surface. The extreme tilt results in unusual seasonal variations. Each pole is pointed toward the Sun for roughly 42 Earth years, leading to prolonged periods of constant sunlight followed by decades of darkness. These long seasons influence the behaviour of the planet's atmosphere, although much of its weather remains hidden beneath the thick cloud layers. Uranus has some of the coldest temperatures in the solar system, with the upper atmosphere reaching as low as -224 degrees Celsius. Uranus is encircled by a faint ring system composed of at least 13 known rings. These rings are narrow, dark, and composed mostly of large particles with minimal dust. The rings are thought to be relatively young in astronomical terms, and possibly formed from debris generated by collisions involving Uranian moons or other small bodies. The ring system was first discovered in 1977, when astronomers observed dips in starlight as Uranus passed in front of a distant star. These dips indicated the presence of rings before they were later imaged by the Voyager 2 spacecraft during its flyby in 1986. In addition to its rings, Uranus has at least 27 known moons. These moons are named primarily after characters from the works of William Shakespeare and Alexander Pope. The 5 largest moons, Miranda, Ariel, Umbriel, Titania, and Oberon, show signs of past geological activity. For example, Miranda has towering cliffs and deep canyons, possibly formed by tectonic forces or resurfacing events. Some of these moons may contain subsurface oceans beneath their icy crusts. However, there is limited data on their internal structures and compositions, so further exploration would be necessary to confirm these possibilities. The only spacecraft to have visited Uranus is NASA's Voyager 2, which flew past the planet in January 1986. During its brief flyby, Voyager 2 captured images and gathered data on Uranus's atmosphere, magnetic field, ring system, and moons. The spacecraft's trajectory took it about 81,500 kilometers from Uranus's cloud tops, providing the most detailed observations we currently have of the planet. Voyager 2 revealed the pale blue color of Uranus, the offset magnetic field, and the ring system that had previously only been detected through indirect means. It also observed the planet's surprisingly bland appearance at visible wavelengths, with few visible cloud bands or storm features. However, more recent studies using infrared telescopes have shown that Uranus does have some atmospheric activity, especially near its poles. Since Voyager 2, Uranus has been observed using space-based and ground-based telescopes, including the Hubble Space Telescope and the Keck Observatory in Hawaii. These tools have allowed scientists to study seasonal changes in the atmosphere and monitor brightness variations that suggest dynamic processes occurring beneath the cloud tops. Despite being a planet of scientific interest, Uranus has not been revisited by another spacecraft since the Voyager 2 encounter. One reason is the difficulty of reaching such a distant object. At its average distance, Uranus is nearly 20 times farther from the Sun than Earth. Any spacecraft launched toward it would take many years to arrive, even with gravity assist from other planets. Another challenge is the lack of sunlight at that distance, which limits the effectiveness of solar power for spacecraft systems. Missions to Uranus would likely require nuclear power sources similar to those used on Voyager and the Cassini mission to Saturn. Nonetheless, there is growing interest in returning to Uranus. The National Academies of Sciences in the United States recently recommended a flagship mission to the Uranus system as a top priority for planetary science. Such a mission could study the planet's atmosphere, magnetic field, rings, and moons in detail, providing insight into ice giant formation and dynamics. Future missions might also include atmospheric probes, orbiters, or flybys of the planet and its satellites. These efforts could transform our understanding of Uranus and ice giants in general. Uranus plays a significant role in the broader context of planetary science. Its classification as an ice giant sets it apart from both terrestrial planets and gas giants. Studying Uranus helps scientists understand the diversity of planetary types, both within our solar system and beyond. The ice giants, Uranus and Neptune, are believed to represent the most common type of exoplanet in our galaxy. Many planets discovered orbiting distant stars are similar in size and mass to these two. Learning more about Uranus could therefore shed light on the properties of a large population of planets that exist in other star systems. Additionally, Uranus's tilted axis, unique magnetosphere, and cold atmosphere offer an opportunity to test models of planetary evolution under different physical conditions. These features challenge existing theories and push researchers to develop more refined explanations of how planets form and change over time. Understanding Uranus also contributes to comparative planetology, the practice of examining planetary systems to identify shared features and variations. This comparative approach helps to answer larger questions about how planetary systems like our own came to be. From Earth, Uranus is just visible to the naked eye under very dark skies. It appears as a faint bluish-green dot and is often best seen through binoculars or a small telescope. Because of its distance, even powerful amateur telescopes can only show a small disk with limited surface detail. Professional observatories use advanced techniques such as adaptive optics to study Uranus in greater detail. Space telescopes like Hubble have captured images showing cloud bands, storms, and the changing orientation of the planet due to its tilt. Long-term observation campaigns monitor the planet's atmosphere and seasonal variations. Astronomers have also studied Uranus by observing how it affects the orbits of other bodies and through occultations, events where Uranus passes in front of a star. These methods have contributed to our understanding of its ring system and allowed for more precise measurements of the planet's size and shape. Though distant, Uranus remains accessible to study and continues to offer clues about the outer solar system and planetary behavior under extreme conditions. Continued observations will be crucial for planning future missions and refining theoretical models. New data from missions like the James Webb Space Telescope and ground-based observatories may provide even more insight in the coming years. These tools allow astronomers to observe Uranus's atmosphere across a range of wavelengths, detecting changes in cloud patterns and storm activity. Infrared observations in particular can reveal temperature differences and deeper atmospheric layers that are not visible in optical light. There's also the potential to use radio telescopes to study Uranus's magnetosphere and its interaction with the solar wind. These observations help to track how the magnetic field responds to charged particles and provide a better understanding of how such fields behave under extreme tilt and offset conditions. Combined with theoretical models, observational data helps paint a more complete picture of this unusual world. As the technology for space exploration continues to improve, the case for revisiting Uranus becomes more compelling. With new instrumentation, a dedicated mission could answer long-standing questions about the composition, behavior, and history of this icy planet. Interest from international space agencies is growing, making a future return mission increasingly likely. Uranus, while often overlooked, remains one of the most intriguing and scientifically valuable destinations in our solar system. In summary, Uranus is a cold, distant planet with the unique tilt, a faint system of rings, and a set of intriguing moons. Its icy composition, offset magnetic field, and subdued internal heat make it a fascinating target for future exploration and scientific inquiry. Though much remains unknown, Uranus offers a chance to explore a type of planet that seems common in the universe, but has only been visited once. Studying Uranus can help refine our models of planetary systems and improve our understanding of how planets form and evolve. As you rest now, let the quiet stillness of Uranus settle into your imagination. Its soft blue light, distant orbit, and slow seasons create a serene rhythm that mirrors the peaceful breathing of sleep. As we move farther from the sun and deeper into the outer solar system, the pace of change slows and we find a moment of calm. Next, we will journey to Neptune, the last of the known major planets, where the winds are swift and the atmosphere holds secrets still waiting to be revealed. But for now, let your thoughts drift gently in the direction of Uranus, steady and calm, beneath a sky full of stars. Neptune is the 8th and farthest known planet from the Sun in our solar system. It is classified as an ice giant, distinct from the gas giants like Jupiter and Saturn. Neptune has a deep blue colour due to the presence of methane in its upper atmosphere, which absorbs red light and reflects blue. The planet was discovered in 1846 through mathematical predictions rather than direct observation, making it the first planet located using calculations. its existence was inferred by astronomers noticing irregularities in the orbit of Uranus. Neptune was later observed and confirmed with telescopes. Neptune orbits the Sun at an average distance of about 4.5 billion kilometers, or roughly 30 astronomical units. One orbit takes about 165 Earth years. Despite its great distance, Neptune plays a significant role in shaping the structure of the outer solar system through its gravitational interactions. This planet is similar in size to Uranus, with a diameter of approximately 49,200 kilometers. However, Neptune has a greater mass, indicating a denser internal composition. It has a faint ring system and numerous moons, some of which exhibit unusual orbits and surface features. In this chapter, we will explore Neptune's atmosphere, interior, magnetic field, ring system, and moon system, as well as its exploration history and broader scientific significance. Neptune's atmosphere is composed primarily of hydrogen and helium, with a small amount of methane. Methane is responsible for the planet's vivid blue appearance. The atmosphere extends deep into the planet, gradually transitioning into a slushy, icy mantle beneath the visible clouds. The atmosphere exhibits strong winds and dynamic weather systems. Wind speeds on Neptune can reach up to 2,100 kilometers per hour, making them the fastest in the solar system. These winds drive massive storms and cloud formations, including the famous Great Dark Spot observed by Voyager 2 in 1989. Cloud bands and bright methane ice clouds are often seen in Neptune's upper atmosphere. These clouds form when rising gas cools and condenses at high altitudes. The atmospheric pressure and temperature increase with depth, eventually leading to a region where the gases begin to behave more like fluids. The temperature at the top of Neptune's atmosphere is approximately negative 218 degrees Celsius, making it one of the coldest places in the solar system. Despite its distance from the Sun, Neptune emits more internal heat than it receives from solar radiation. This internal heat drives atmospheric circulation and contributes to its weather patterns. The origin of Neptune's internal heat is not fully understood, but may be due to gravitational contraction or the slow release of residual heat from the planet's formation. Neptune's internal structure consists of three main layers: a dense core, a thick mantle, and an outer atmosphere. The core is composed of rock and metal and is estimated to be about 1.5 times the mass of Earth. Surrounding the core is a mantle made primarily of water, ammonia, and methane ices. This region, under high pressure and temperature, may exhibit properties of both liquids and solids. The outer layer is the atmosphere, which gradually transitions into the underlying mantle without a well-defined boundary. This structure is typical of ice giants and differs from gas giants like Jupiter, which have a more extensive envelope of hydrogen and helium. Neptune's internal heat contributes to its dynamic weather systems. The heat likely originates from the gradual contraction of the planet over time, releasing gravitational energy. Unlike Uranus, which radiates little heat, Neptune emits more than twice the energy it receives from the Sun. The high internal pressure may also lead to unusual physical states. Some models suggest that within Neptune's mantle, carbon atoms may form diamond crystals that sink toward the core, a phenomenon known as diamond rain. Understanding Neptune's internal composition and structure provides insights into the formation of ice giants and the behavior of materials under extreme conditions. Neptune has a strong and irregular magnetic field that is tilted by about 47 degrees from its rotational axis and offset from the planet's center. This magnetic field is believed to be generated by the motion of electrically conductive fluids in the mantle, possibly a mixture of ammonia and water. The magnetic field creates a complex magnetosphere that interacts with the solar wind. As the planet rotates, the magnetosphere wobbles, producing dynamic auroras and variations in radiation belts. Neptune completes one rotation approximately every 16.1 hours. This rotation period has been determined using radio emissions from the planet's magnetic field. Like other giant planets, Neptune exhibits differential rotation, with equatorial regions rotating at different speeds than the poles. The rapid rotation contributes to the planet's slightly flattened shape, with a bulge at the equator. It also influences atmospheric dynamics, including the formation of jet streams and storm systems. The interaction between the magnetic field and solar wind leads to auroral activity near Neptune's poles. These auroras differ from those on Earth because they are shaped by the planet's offset magnetic field and are not necessarily aligned with the rotational axis. Studies of Neptune's magnetic field provide clues about the internal composition of the planet and the behavior of conductive materials under extreme pressure and temperature. Neptune has a faint and dark ring system composed primarily of dust particles. The rings are named after astronomers who contributed to the study of Neptune: Gall, Leverrier, Lassell, Arago, and Adams. These rings are not as prominent or bright as those of Saturn. They are likely composed of dust and small rock fragments, possibly originating from collisions involving Neptune's moons or debris captured by the planet's gravity. The rings contain clumps and arcs, which are regions of higher particle concentration. The arcs are maintained by gravitational interactions with nearby moons, particularly Galatea. These features are unusual and suggest a dynamic and evolving ring system. Neptune has 14 known moons. The largest, Triton, is unique in the solar system due to its retrograde orbit, which means it orbits Neptune in the opposite direction of the planet's rotation. This suggests that Triton was likely captured by Neptune's gravity rather than forming alongside the planet. Triton is geologically active and has a thin atmosphere primarily composed of nitrogen. It features cryovolcanoes that eject frozen material, likely a mixture of water, ammonia, and methane. The surface is varied, with smooth plains, ridges, and frozen lakes. Other moons, such as Nereid and Proteus, also exhibit interesting features and orbits. These moons contribute to the understanding of Neptune's gravitational influence and history. Neptune has only been visited by one spacecraft, Voyager 2, which conducted a flyby in August 1989. This mission provided the first close-up images of the planet and revealed many details about its atmosphere, rings, and moons. Voyager 2 discovered the Great Dark Spot, a massive storm system in Neptune's southern hemisphere. It also captured images of bright clouds and atmospheric bands, along with measurements of wind speeds and magnetic field characteristics. The spacecraft observed Neptune's ring system and several of its moons, including Triton. These observations significantly expanded knowledge about the outer solar system and highlighted the need for further exploration. Since Voyager 2, observations of Neptune have been made using ground-based telescopes and space-based instruments, such as the Hubble Space Telescope. These observations have tracked changes in cloud patterns, atmospheric dynamics, and the behavior of the ring arcs. Plans for future missions to Neptune have been proposed, including orbiters and probes that could study the planet and its moons in greater detail. These missions aim to address questions about the planet's interior, magnetic field, and potential habitability of moons like Triton. Continued observation and exploration are important for refining models of planetary formation and understanding the diversity of planetary systems in the galaxy. Neptune's structure and composition provide a reference for understanding ice giants. a class of planets that may be common in other planetary systems. By studying Neptune, scientists gain insights into the physical and chemical processes that govern planets with icy mantles and hydrogen-helium atmospheres. Comparative planetology involves analysing Neptune in the context of other solar system bodies. Differences and similarities between Neptune, Uranus, and the gas giants offer clues about their formation histories and internal dynamics. Neptune's weather systems challenge existing models of atmospheric dynamics. The extreme wind speeds and persistent storm features require a deeper understanding of fluid behaviour under low temperatures and high pressures. The planet's ring system, while faint, helps researchers examine the longevity and evolution of ring structures. Its interactions with moons and external forces provide examples of orbital resonance and gravitational sculpting. Triton's retrograde orbit and geologic activity raise questions about the origins and potential for subsurface oceans. If confirmed, these oceans may have implications for astrobiology and the conditions needed for life. Neptune's magnetic field, which differs significantly from Earth's and Jupiter's, provides data for testing theories about dynamo processes and the generation of magnetic fields in planets with non-metallic interiors. Advances in telescope technology have improved the ability to observe Neptune from Earth. Adaptive optics and high-resolution imaging allow astronomers to study its weather systems, atmospheric composition, and ring structure in greater detail. Observations in the infrared and radio wavelengths help probe Neptune's deeper atmospheric layers. These studies support models of convection, heat transfer, and chemical distribution within the planet. Neptune is also used as a benchmark when examining exoplanets. Ice giants are thought to be common in other star systems, and understanding Neptune helps interpret data from distant worlds with similar mass and size. Data from Neptune assist in modelling planetary system formation and migration. The current positions and compositions of Neptune and other outer planets suggest that they may have migrated from their original orbits due to gravitational interactions. These insights are used in simulations that aim to reconstruct the early solar system and apply those findings to other systems observed by telescopes like Kepler and James Webb. By continuing to observe Neptune, astronomers refine their understanding of planetary physics, atmospheric chemistry, and orbital mechanics. Each new observation contributes to a more complete picture of our solar system's history and structure. Neptune, the most distant planet in our solar system, offers a wealth of scientific interest. With its strong winds, dynamic atmosphere, unusual magnetic field, and icy interior, Neptune challenges conventional models and encourages deeper investigation into the nature of planetary bodies. Its ring system and collection of moons, especially Triton, expand our understanding of gravitational interactions, surface geology, and orbital dynamics. The planet's composition helps scientists explore the boundaries between gas and ice giants and provides context for exoplanetary studies. Although visited only once, Neptune continues to be a focus of astronomical research. Each observation reveals new details and raises questions that drive future exploration. With upcoming missions and improved observational tools, our understanding of Neptune and its role in the solar system is likely to grow. In this chapter, we have covered the key aspects of Neptune's structure, atmosphere, magnetic field, and satellite system. These elements contribute to the broader knowledge of planetary science and deepen our appreciation of the complex and varied worlds within our cosmic neighbourhood. As we leave Neptune and prepare to move beyond the planets into the Kuiper Belt, we carry with us the lessons learned from this cold, windy, and beautiful world. Neptune's continued study highlights the importance of long-term observation in understanding planetary behavior. Every storm, magnetic fluctuation, or cloud formation observed helps build a more complete model of this distant world. As we refine our tools and develop new missions, Neptune remains a key piece in the larger puzzle of solar system science. In the late 1970s, NASA launched 2 spacecraft that would become the farthest-travelled human-made objects in history, Voyager 1 and Voyager 2. These missions were designed to take advantage of a rare planetary alignment that allowed for gravity-assisted flybys of the outer planets. Originally expected to last about 5 years, the Voyager spacecraft have continued to operate for over 4 decades, transmitting valuable data from the far reaches of the solar system and beyond. The primary mission was to conduct close-up studies of Jupiter and Saturn, their moons and their ring systems. Voyager 2 was also tasked with visiting Uranus and Neptune, making it the only spacecraft to have encountered all 4 of the gas and ice giants. After completing their planetary tours, both spacecraft continued their journeys into interstellar space, entering what is now known as the Voyager Interstellar Mission. These spacecraft are not only technological achievements, but also scientific instruments that have reshaped our understanding of the solar system's outer regions and the boundary between the solar wind and the interstellar medium. During their primary missions, the Voyagers provided detailed data on the outer planets and their moons. At Jupiter, Voyager 1 and 2 revealed complex cloud structures, volcanic activity on the moon Io, and faint ring systems. These discoveries challenged previous assumptions and highlighted the dynamic nature of the Jovian system. At Saturn, the spacecraft studied the planet's extensive ring system in detail. They also captured images of moons such as Titan, where Voyager 1 observed a thick atmosphere composed primarily of nitrogen and methane, an environment thought to resemble early Earth in some respects. Voyager 2 continued on to Uranus and Neptune. It found that Uranus emits little internal heat and has a tilted magnetic field that does not align with its rotational axis. Neptune was revealed to have unexpectedly strong winds and a large dark storm, similar to Jupiter's Great Red Spot. Voyager 2 also discovered several new moons and ring structures around these planets. These planetary flybys expanded our knowledge of the outer solar system and provided critical data that continues to inform modern planetary science. Voyager 1 became the first spacecraft to enter interstellar space in August 2012. It crossed the heliopause, the boundary where the solar wind is stopped by the interstellar medium. This transition marked humanity's first direct exploration of space beyond the influence of our Sun. Voyager 2 followed in November 2018, confirming many of the observations made by its twin. Both spacecraft recorded changes in particle density, magnetic fields, and cosmic ray levels, confirming their entry into interstellar space. These measurements help scientists understand the structure and behavior of the heliosphere, which acts as a protective bubble around our solar system. Even in interstellar space, the Voyagers continue to send back data. They monitor galactic cosmic rays and the magnetic environment beyond the Sun's influence. These findings help researchers understand how our solar system interacts with the surrounding galaxy. Despite their great distances, over 15 billion miles from Earth, both spacecraft maintain contact with NASA via the Deep Space Network, a global array of large radio antennas capable of receiving faint signals. Each Voyager spacecraft carries a copy of the Golden Record, a 12-inch gold-plated copper disc containing sounds and images intended to portray the diversity of life and culture on Earth. This record is designed as a message for any intelligent extraterrestrial life that might one day find the spacecraft. The record includes 115 images depicting humans, animals, architecture, and landscapes, along with a variety of natural sounds such as thunder, birdsong, and ocean waves. Spoken greetings in 55 languages are also included, along with musical selections from different cultures and time periods. The record's cover includes symbolic instructions for playback and diagrams indicating the spacecraft's origin in our solar system. The concept was developed by a team led by Carl Sagan, who hoped the record would serve as a time capsule representing humanity at a specific moment in time. Though the chance of discovery is extremely low, the golden record represents a gesture of curiosity and outreach, a way of extending human presence into the cosmos, even if only symbolically. As their power supplies decline, both Voyager spacecraft have begun shutting down non-essential systems to conserve energy. NASA expects that by the early 2030s, all instruments will cease functioning and the spacecraft will go silent. Despite this, they will continue on their respective trajectories indefinitely. Voyager 1 is moving toward the constellation Ophiuchus and will pass within 1.6 light-years of the star Gliese, 445 in about 40,000 years. Voyager 2 is headed in the direction of the constellation Sagittarius. Neither will approach any star closely for tens of thousands of years. Once their onboard systems are no longer operational, the Voyagers will become silent artifacts travelling through the galaxy. They will not slow down unless acted upon by another force, and could continue to drift for millions of years. In this way, they serve as time capsules of human civilization, carrying with them a record of our presence in the universe. These spacecraft remind us that even small machines launched from Earth can reach into the vastness of space and continue their journey long after our lifetimes. The Voyager missions have fundamentally reshaped how we understand the outer solar system and interstellar space. Their longevity and continued performance have exceeded expectations, providing data that was once thought to be unreachable with mid-20th century technology. From revealing active volcanoes on Io to measuring the density of interstellar plasma, Voyager has contributed to fields ranging from planetary geology to astrophysics. Its observations have informed numerous missions that followed and set benchmarks for long-duration spaceflight. As sleep-friendly content, the Voyager story invites quiet reflection. These distant spacecraft, still travelling in the silent dark, offer a sense of continuity and perspective. They illustrate the scale of the universe and the persistence of exploration. One signal, travelling slowly back home. As we conclude this chapter, imagine the Voyagers still out there, quietly drifting beyond the reach of the sun, recording faint data and holding on to a record of our world. Though they may one day fall silent, their journey endures in the minds of all who dream of the stars. As our journey comes to a close, we gently drift back from the edge of the solar system. From the warmth of the sun to the cold frontier of interstellar space, we have moved through a landscape of planets, particles, and profound discoveries. Each stop along the way offered a different glimpse into the workings of our cosmic neighbourhood. We began with the sun, the engine of life and energy, examining its constant fusion reactions and solar wind. From there, we visited Mercury and Venus, observing their extreme temperatures and atmospheric contrasts. Earth, our home, stood out with its blue oceans and protective magnetic field. Mars followed, its red terrain shaped by winds and ancient water. We explored the gas giants, Jupiter and Saturn, with their deep atmospheres and complex moon systems. Uranus and Neptune revealed magnetic anomalies and distant storms. Finally, we followed Voyager to the heliopause, the boundary that separates us from the galaxy beyond. This entire journey was not only a tour of physical objects, but a way to connect with our place in space. You have travelled billions of kilometres while resting in the quiet of your room. Now, let us return slowly to a state of rest. You are no longer moving through space. You are here, grounded, supported by gravity and surrounded by silence. The vast distances we explored are real, but so is this quiet moment. Take a breath, deep and slow. Let your body sink a little deeper into whatever holds you. There is no rush, no need to go anywhere. Your thoughts may continue to wander through the stars, or they may settle like dust in a low-gravity world. Either way is welcome. You are safe. You are still. You are part of something much larger, and yet you're also completely at ease in this present moment. Allow your breathing to guide you, steady, gentle, and calm. If your mind drifts, you can bring it back to the feeling of rest. Like a spacecraft reaching orbital stability, you are in balance now. In the vastness of space, every particle is connected by gravity and energy. In your life, you too are connected to people, to ideas, to the unfolding of time. Even as you rest, you remain part of the world and its rhythms. You are allowed to rest. You are allowed to pause. You are allowed to find peace in stillness. Let your mind release the tension of the day. Any unanswered questions or lingering concerns can wait. This time is for healing, for comfort, and for calm. Know that your curiosity is a gift. Your ability to wonder, to explore, to imagine. These are deeply human qualities. As you sleep, those parts of you remain present, gently processing, quietly dreaming. There is no need to be anywhere else. You are enough just as you are. In stillness, you are whole. As we close this chapter, know that the universe continues on, with or without our attention. Stars burn, planets orbit, and cosmic particles drift between galaxies. But right now, none of that requires your focus. What matters most is that you are resting, that your breath is steady, that your thoughts are quieting, like signals fading into the background radiation of space. This moment is yours and you have earned it. You've journeyed through the solar system with attention and care. Now the body can rest and the mind can sleep. Should you awaken in the night, know that you can always return to this space, this place of calm and understanding. The cosmos is not in a hurry, and neither are you. Let yourself go softly and slowly into the gentle rhythm of sleep. You are connected to a universe that continues to unfold moment by moment in both vast and intimate ways. Sleep is not a failure of activity. It is a vital part of your cycle, like the orbit of a moon or the spin of a distant planet. In sleep, your body regenerates, your mind restores, your emotions settle. You do not need to do anything but allow it to happen. Let the tension release from your shoulders. Let the muscles in your face soften. Let your breath find a natural rhythm. No effort, no urgency. Whether you drift off now or in a few minutes, you're moving in the right direction. Toward calm, toward sleep, toward quiet. You are part of the cosmos, and the cosmos is patient. There is no rush here, just stillness. Soon, your breathing will deepen, and your thoughts will become less defined. You may begin to feel weightless, as though floating in orbit. There is nothing you must remember, nothing you must solve. You're not required to do anything right now except rest. The body knows what to do. The mind, too, will follow. Like a spacecraft that has shut off its engines, you are in free drift, peaceful and sustained. This audio will fade, but your sleep will continue. If you are already asleep, that is perfect. If you are on the edge of sleep, know that the next breath may take you there. Thank you for travelling through the sleepy cosmos. The journey continues in your dreams, in your breath, and in the calm, repeating pulse of your heartbeat.